This lesson's on the product rule. It's a useful rule that extends the expressions and equations we're able to differentiate. Specifically, as you can see from the lesson aims, when we've come to terms with the product rule, we'll be able to differentiate where an expression can be written as one function of x times another function of x. In other words, a product of two functions of x. It's important with the product rule that we recognise when to use it. We use it in this situation here and not where we've got a composite function, a function of a function like this, which is where we use the chain rule. We'll look in a bit more detail about examples of using the product rule in a minute. Before we do, let's have a quick recap on what you should know already. So if you pause this presentation and have a go at the question that's on here, using the techniques that you've learned previously for differentiating using the chain rule and differentiating natural log functions. Okay, hopefully that was successful. I'll run through it quickly. Okay, so the key to differentiating functions like this is to use the chain rule. I'll just write down the chain rule, which is dy dx equals dy du times du dx, where u is the chaining variable. So we start off by making the substitution equals the inner function up here, which is the 7x minus 13, the bit in brackets, which then implies that our original function changes from y equals ln of 7x minus 13 to y equals ln u. We now have two separate equations, u equals and y equals, both of which we can differentiate. This one here, we differentiate with respect to u, so dy du, and you should remember the result, ln u will differentiate to 1 over u. If not, go back over the how to differentiate natural logs lesson. This one here, it's du with respect to x, and we just get 7 and the minus 13 goes to 0. Right, let's remember our chain rule here. We've now got the bits we need. So dy dx equals dy du, which is 1 over u. Well, we can substitute the u back because we want everything in terms of x. So that's 7x minus 13, and then times 7. And then we would just write that as 7 over 7x minus 13, and hopefully you can see from that that it's actually just the derivative of the inner function up here, this inner function, over the inner function itself. The question asks us to find the equation of the tangent to that curve, so we've differentiated to find the gradient function. We're told that x equals 2. Well, if x is 2, then we get y equals the natural log of 7 times 2, 14, minus 13, which gives us y equals ln 1, which is 0. So y is 0, x is 2. So what we do next is we use the equation y minus y1 equals m x minus x1. So that gives us, well, y minus 0, because we've determined that y is 0, so y equals m. Well, our m is our 7 over 7x minus 13. Well, again, x is 2, so if we put the 2 in there, we just get 7 there, don't we, because it's 7 over 1. And then x minus x1, which is 2, and the equation generally would be fine in that form, but we can write it as y equals 7x minus 14 in y equals mx plus c format. That was an exam question, and you can see the marks here for finding the gradient function. There's 2 marks, an n mark and an a mark, and then finding the equation. And as I suggested, you could have left it in that format. It doesn't actually ask for it in y equals mx plus c or anything, so that would have been absolutely fine. Okay, so we can now start thinking a bit more about the product rule. This gives you a little bit of an idea. We've learned various different methods of differentiation. These type of problems, we can use the straightforward core 1 differentiating technique to find the derivative of an equation like this. We need the chain rule for an equation like this. We now know how to differentiate natural log and exponential functions, but so far we don't have any method for these products of 2 functions of x. And here's an example. You might have something like x times the natural log of x squared. There's an example where you have a product. Currently then we don't have a method for doing that, which is where the product rule comes in.